All right, awesome. And we are live. We'll give people a minute to hop on, but I see that Ravit has already joined this morning. Thanks for hopping on, Ravit.
Nice.
That's nice. It lets me know that the comments are working before we even start. Okay, perfect. So I am just going to start. Welcome to the Cool Data Project Show. I'm Kristen Kerrer, a developer advocate for Comet, where with one function you can make your ML models. Oh my God. You know what? I'm just going to start completely from the beginning. Welcome to the Cool Data Project Show. I'm Kristen Kerrer, a developer advocate for Comet ML, where with one function you can make your ML runs reproducible. And the Cool Data Project Show is where I interview practitioners in MLDL AI and ask them all about the methodology of the projects that they're working on so that we can all learn together. My guest today is DJ Sakar. Super excited to have him. I've known him for a couple years now, and he's actually created a really cool presentation to share with us. So, DJ, could you introduce yourself and tell us a little bit about SIT Academy?
Yeah, hi everyone. Great to be here. I'm DJ. Many of you might know me. I love sharing different aspects of data science with the community. I'm working as a lead data scientist in SIT Academy. SIT Academy is focused on two main things. One is we run data science and full stack programs, typically for professionals, so that they can upskill in different areas of be it data science or software engineering, kind of pivot their careers. We also do consulting projects with companies with regard to data science or software engineering. That's where we work on an end-to-end project, do some prototyping and so on, and make sure that some good value is realized at the end of the prototyping process.
Awesome, awesome. And so, what was the motivation for the project that you're going to share with us today? Can you tell us a little bit about that?
Absolutely. So the project is called Satellite Image Super Resolution. You should probably get what it means from the name itself. The whole idea is working on satellite imagery, taking low resolution satellite images and leveraging generative deep learning for computer vision to transform it from a low resolution image to a high resolution image. The motivation for the project was it was actually a final capstone project, which is typically done in collaboration with the industry. So a couple of our students worked on this project, and we worked on this project with association with SIT and South Pole. So the project came from South Pole, and the idea was to see how we could leverage satellite imagery to improve resolution of the images. It actually started out as a hobby project for me, like image super resolution, and it was super interesting that we could leverage the exact same code and achieve really good performance in the real world.
Oh no, people are saying that there is an echo.
Oh, there's an echo.
Okay. The echo cancellation is on.
Okay.
I'm not sure what to do about that. Oh, they said it's on DJ's end. What if I... do that? DJ, you want to say something?
Yeah.
Oh,
Should I join back in? I'm using the same headphones actually. If it's the settings.
Okay, so I just turned on echo cancellation on the main thing. Can someone comment again right now and let me know if it's any better? I'm not hearing myself anymore.
What about me? There's some echo. Not a
Oh,
lot
you're
though.
still hearing it on your side?
Not a lot for me. I don't know about the audience.
Okay, so we'll see if another comment comes through. But so DJ, I know you've written, and I'm sorry I didn't tell you I was going to ask this question ahead of time. But so
Yeah.
it sounds like you do a lot, right? Like you wrote a whole book about NLP, and so that has probably been your main focus for a long time. Like, how long have you been in super? Oh, nice! Somebody said it's good now. Awesome.
Okay.
How long have you been working with like super image resolution, and how much time have you spent studying that?
So there's a lot of research out there on super resolution, like so many papers. We'll cover a bunch of models also probably today when we talk about it. It took me a while. I mean, it took me at least several weeks to understand the models because like I had to understand the research paper first, which is not an easy task. I had to look for tutorials or rather, let's say articles or videos explaining some of the papers because I mean, honestly, I don't know how other people might do it, but if I read a research paper just once, I don't get it, right? I have to read it several times, I have to understand it, and then I kind of get an idea of, okay, how is it working? Then I had to look if there is an existing code implementation. In many cases, it was there. Then I had to make sure it's running because often you have code from a research paper, but it doesn't work well on real world data. So overall, I think the process took close to a month. But then it was working well. I had to do quite a lot of fine tuning, and yeah, I mean, we actually deviated a bit from the paper, which was interesting because we added our own twist, and we got a
Nice.
really nice model. Yeah.
Awesome. Awesome. And then, so do we want to hop right into your demo?
Yeah, I'll go through the presentation, kind of cover what it's all about. Then maybe we can even see some code. Hopefully, people will be interested to see that as always. So let's see.
Oh,
Share my
and
screen.
Ravi says it's very nice to see you.
Yeah, I mean, we chat from time to time. It's always been difficult, but excited for him to be here. Yeah, let's see. Okay, sharing the screen. I'll bring up the presentation. Hopefully it is visible. Let me know.
Yep. No, I see it. It's perfect.
Great. So yeah, this is a project in collaboration with SIT Academy and South Pole. The project actually came from South Pole. The idea was super resolution for satellite imagery. What is the objective? The actual objective, like this is not really a hobby project. This is a real world project where the objective was to assess the impact of climate action interventions like let's say reforestation or sustainable farming practices, as well as trying to see that are there certain areas in the world where due to things like deforestation or as you know, right, building factories and so on, that nature itself is getting affected. South Pole provides consulting for companies, governments, and so on to implement basically sustainability in different aspects like climate action, carbon emission reduction, and so on. The method of this project, what we actually tried to implement was to compare satellite images in given areas, like let's say the Amazon rainforest, right, and so on, to compare satellite images in these areas before and after a certain intervention. That okay, what has happened in this area over the course of 10 years? Did the forest cover reduce? Then something needs to be done there, right? Like reforestation, maybe. So that was the main objective, and this is a clear example which kind of shows you, taken again from actual data. On the left hand side, you see that within the course of a year, right? Within the course of a year, this forest area has been completely cut down and roads and other stuff are coming up. So the whole point here is, can we look at such regions of the Earth in terms of satellite imagery, and then take necessary action so that at least activities like excessive deforestation and so on, they can be reduced. Now, coming to the business problem, that okay, what is it all about? Super resolution, like how does it tie to this problem? So, what's happening here is if you want to go back, let's say beyond 2017, and let's say you want to compare what's going on in a certain region, these images are typically available from Google Earth Engine's Landsat satellite imagery. Now, Landsat data is usually low resolution. It is not as high resolution as the newer satellite imagery data, which comes in from, which comes in from Sentinel-2. As you can see, right, the images from Sentinel-2 are quite well in terms of resolution, quite high resolution, but imagery from their other satellite, the Landsat 8, that is not as good. So the idea is, okay, if you want to compare, let's say, a certain region on Earth from satellite imagery data from, let's say, 2015, and compare it to 7 years later in 2022, it won't be an apples to apples comparison, right? Because this is low resolution, this is high resolution. So the idea is, can we use super resolution on these low resolution images to bring it up to a level so that we can do an apples to apples comparison with the high resolution images from Sentinel-2. That is one thing. Plus, also the other reason for doing this is they want to study the effect of what's happening on the planet, let's say several years back, by looking at those images in detail with the high resolution, and then see, okay, what's happening over the course of time. So now coming to the technical aspects. So the technical aspects of this is we wanted to leverage super resolution by using deep learning models for computer vision. The overall focus is you have an image which is low resolution. You have, let's say, corresponding images in high resolution. Now, how can you do that? There are some things which you could do. You take high resolution images, which are already there. You do some downsampling or maybe add some noise to it and create low resolution versions of those images. In that way, you have low resolution and high resolution images. And then you pass it through this model, let's say, which is a bunch of CNN layers, along with some other things, which I will talk about when we go into the model architecture specifics. And then what we do is we make the model generate a completely new image. So this is just like what a GAN does, right? A generative adversarial network, which is typically used to generate images or generate data. Nowadays, we have the models like stable diffusion and so on, right? Where you write in some text, it generates a whole image. So kind of similar principles here, where we generate a image which is supposed to be a super resolution or a better resolution version of the low resolution image. We compare it with the high resolution image, and we try to bring the generated image as close to the ground truth, the high resolution image, as possible. So overall, that is the focus of trying to make this network generate a really high quality version of a low resolution image. So remember that super resolution image is just a function of low resolution, where the function is nothing but your generative deep learning model.
Does that mean there's two satellites? So like one's getting high resolution images and one's getting low resolution, and are they taken at the same time? Like
if you're after 2017, then yes, you can kind of get it from both of them. If you are before 2017, then you will not get the high resolution one. So that is where, let's say, if you want to compare a particular region in 2015 versus 2022, you can get the high resolution from this one, but you cannot get a high resolution of that area from 2015. That you can only get from Landsat. And that is where we have to use our model to make it better, basically.
Okay, so you're making historical images better with high resolution new images.
Exactly, because what we could do is we could convert these into bad resolution, right? Convert these into low resolution with downsampling and then train the model. So that is how we generate data to train the model, yeah, or fine tune, I would say, yeah. Okay, so that is what super resolution is all about, transforming this kind of, you can see a lot of artifacts here, blurring and all that, low resolution into better resolution. These are the models which we have actually used. You can even go back to the recording later on, maybe, and Google some of these. The papers are available. Typically, the paper names are actually here. So these are actually all the models which were explored, starting with residual dense network, RRDNs, EDSR, and then SRGAN. SRGAN, super resolution GAN, actually uses a model called super resolution ResNet, but we did not use that. We actually modified this network by using transfer learning to fine tune an EDSR. So I'll talk about that as we go into details. But yeah, it was definitely an interesting exercise and also super intensive. And given that we had a short time to do the prototyping for this project, luckily that is where my hobby project and the expertise came in handy to basically churn it out faster.
What's a short time for the project?
So typically these projects are more like capstone or final projects, which are often done towards the end of the program. And usually you can say it is around 3 to 4 weeks if you want to think about it in that way. So the idea is to finish up the prototyping within that time frame and then do a presentation and a final presentation to the client, or in this case, the stakeholders, which were South Pole.
All right.
Yeah. I mean, in the real world, also, if you're working in a company, typically for a prototype, usually you would get around a month. I mean, they wouldn't wait
Mm-hmm.
6 months to for you to come up with a model. So, yeah, kind of
No.
trying to emulate that scenario.
Mm-hmm.
Okay, so a bit about the models. Residual dense network, very interesting. One of the initial models which came out for super resolution. As you can see, it is a layered architecture. And those of you who know about models like ResNet, if you remember, that is where these concepts like skip connections got introduced, right? Where features from the initial parts of the network could go into the later parts of the network so that the model doesn't lose out a lot of information after all the downsampling and pooling and whatnot. And also the gradients can flow back better to prevent issues like vanishing gradients. So those principles are seen in all of these models. Residual dense network proposes residual dense blocks, which itself is a stack of conv layers, a bunch of dense connected convolution layers. And as I mentioned, it allows direct connections towards the later parts of the network. Uses something called global feature fusion, which is just combining the older and the newer features together to learn from that. And ultimately, again, the focus is to generate this high resolution image from the lower resolution image. So this was one of the models we started with. Then we went one step further, which is residual in residual dense networks. Why is it called that? Because you see this network, which is the high level architecture where you have a low resolution image. The idea is to generate a high resolution version of it. And you have these blocks inside it. So you see there are some global skip connections here, again, to propagate better gradient flow and features from initial parts to the deeper parts of the network. And it is called residual in residual dense because each of these blocks themselves are a bunch of layers with residual connections. So basically, each sub part of the network has residual connections, and the global network itself also has residual connections. Now, what they had proposed was before this, there was an architecture where there was a bunch of batch normalization and other layers. So they mentioned that using or rather removing some of those layers ends up making the network not just faster, but uh, more stable. So that was one of the findings of that research paper, and hence we tried this model also. And the way they train this model is again with a GAN, where this is used as a generator, and they have a discriminator network also, which helps in basically saying whether your image is fake or not. In this case, it is whether the image is uh, close to the super resolution, or rather the high resolution ground truth or not. So that is another model which we used. And then we went into more complex models. And actually, these are some of the models which we ended up using finally because they gave the best performance. So this one also you can search online. This is called as EDSR networks, Enhanced Deep Residual Networks. This is where, again, if you see The initial research papers which came out on super resolution, they had a bunch of stuff with a lot of batch normalization layers. So this is where they proposed to again remove these batch normalization layers and improve the performance of the model. And overall, this is the architecture where they are doing some downsampling, upsampling, some shuffling. But overall, again, the architecture is very similar to regular CNNs with convolution networks followed by activations and so on. And the idea, again, is same, generating a high resolution image from a low resolution image. And what we then did was go for what was kind of state of the art in super resolution, which is called SRGAN. This was actually the first model which was able to basically create super resolution images up to upscaling factor of 4x. And this is where they introduced this novel concept of a perceptual loss function, which has your regular adversarial loss, which the discriminator uses to distinguish between fake and real, in this case, super resolution compared to high resolution, and also content loss. The content loss is very interesting. I will talk about that even maybe later when I go through the code a bit more, where they actually use features from a VGG model to compare between super resolution and high resolution. But we did not use the network proposed for this model, which was known as SRR net, super resolution ResNet. We used this EDSR model, which we actually pre-trained on a bunch of data. And then we fine-tuned that EDSR as a generator in this overall SRGAN discriminator network. Okay, so we leveraged transfer learning where we use this pre-trained EDSR model, which I mentioned earlier, and then we fine-tuned it using the SRGAN discriminator, just like a normal GAN. So that actually gave us better results. And maybe I will show one example here. So let's say this is Landsat, this is Sentinel. Now, this is like bicubic interpolation. This is residual dense network, RRDNs, and this is the final combination. So you can see that, I mean, of course, it is not perfect, but from a really bad resolution, we can really improve the resolution of this image so that we can at least compare it to an actual high resolution image, basically trying to make it as close to that as possible. So yeah, that's basically like the overall journey of what we took to get to this level. Yeah.
So when you say a 4 times upscaling factor, does the image have to be really poor to have the ability to get that type of improvement?
No, I mean not necessarily. In our, I mean that is what is proposed by the paper, but in our case, the idea is, I mean, if it's really poor, of course, we will struggle because in our case, again, we didn't have a lot of data and we were fine tuning it. But the overall idea is, yeah, I mean, even if it is like distorted to some extent, it will work decently. But yeah, it's not like you have to forcefully get to that level just to make the network work. Yeah. Okay, so just a brief on the workflow. These were the 3 main steps. For the data collection, we actually use the Python API for Google Earth Engine. You can give certain coordinates there, like, okay, select some forested regions like Brazil, Honduras, Madagascar, and so on. The data which you obtain from the satellite is actually not super clean. So, I mean, initially we were hoping that, okay, get the images, as you often see in tutorials or anywhere else, right? That, okay, images, basic pre-processing, build the models, right? That's what we usually see here. Yeah, we had to do a lot of data cleaning, which we were not expecting that, okay, we would have to do, but we had to kind of apply different filters to make sure that the time frame was same. If there was cloud cover, there are ways to remove that layer of cloud cover from the satellite imagery. If there was black pixels, maybe we do some interpolation on that. If there is too much of like black pixels, we would have to discard those images. And besides that, of course, the standardization with regard to scaling, resizing, and all that. But yeah, definitely a fair bit of pre-processing had to be done. And as I said, like we had around 800 images because it does take some time to get those images from the API. Then we tried out the different models, as I mentioned. How we did it was we tried to pre-train the models on the diff2k dataset, which is a benchmark dataset we use for super resolution, and then we tried to fine-tune on our data, try out different models, tune with the regular hyperparameters, and try to see what gives us the best results. We tried out different metrics. Actually, I will probably share the GitHub repository so that maybe people can check it out in more detail. But we tried different metrics to see which model gives us the best result finally. And yeah, that's pretty much the project details in terms of what we did. Overall, SRGAN seemed to give us the best performance. The idea is, but it can still be removed because I've seen some transformer-based architectures come in for super resolution. So the idea would be to maybe try some of that later on. And that's about the presentation. Thanks to the team, the folks who worked tirelessly on this. And yeah, we can discuss in more detail, and maybe I can show some code also whenever necessary. Yeah.
Yeah. Do you want to just hop right into the code?
Yeah, why not? Absolutely. Let me try to see if I can bring that up. Let me know if you can see it.
Yeah, that looks good to me.
So this doesn't have the satellite imagery, but this has the exact model we use. This is the, you can say, improved version of one of the notebooks from my hobby project. So yeah, I worked on this ages back. This cell hasn't still been removed, so you can see probably I ran this around 2020, right? So yeah, definitely it's been a while. So we use TensorFlow for this. In this case, that was the main framework of choice. Although some of the newer models you can easily implement in PyTorch also. This is the data set we used in general for the initial pre-training of the model. Okay, because we are going for transfer learning, I will just click on this so you can see this. This is known as the diff2k data set. This is often used for a lot of the challenges for super resolution, as well as often one of the benchmark data sets, which people typically use to test their super resolution models before releasing research papers. There are different scales available here. Okay, by scale I mean like different sizes of the images and different scaling factors in terms of super resolution. Okay, so like how much they have been downscaled by. Okay, 2x, 3x, 4x, and so on. So we are using the 4x version of the data set. The good part here is you have, of course, the high resolution image, the ground truth, and your low resolution version of the same image. And you want to make the model learn to transform that low resolution into the high resolution or as close to the high resolution as possible. We load up the data, make sure we convert it into some TensorFlow data set so that we can easily load up the images in a batch mode rather than like load all the images in memory in NumPy arrays. Okay, so that is where we use TensorFlow data sets and basically transform the image from a PNG into a tensor. Tensor is just a fancy term for a NumPy array. It's not exactly a NumPy array, but the structure is similar. We do some processing operations because the images are actually huge to an extent, and also we want to generate as much data as possible. So we take crops of the images, which means if the size of the high resolution is 96, let's say 96 cross 96, the low resolution will be 24 cross 24. Okay, and then the idea is, can you make it into that high resolution image? Okay, so this piece of code helps us in creating those low resolution to high resolution pairs. We do basic augmentation here of just random rotation by 90 degrees or flipping horizontal or vertical. That's pretty much it. Okay, we don't do additional augmentation steps, though you could try it if you wanted to, but we keep it very simple here.
What library are you using for the data augmentation?
Just we just use direct TensorFlow code here.
Okay.
No specific libraries, but you could. I mean, this is where these newer libraries like albumentations and so on could come in
Hmm.
handy. I think a lot of other libraries are also there, right? Where you just call 1 or 2 lines of code and they'll do all this for you. So you don't need to then literally write all this low-level code. Yeah.
Perfect.
Then we set the batch size, create our training data set, ready to basically load in a batch mode of 16 images at a time and do the augmentation as necessary. Then we create the EDSR model generator, okay, which will be used later in the GAN architecture. And this is where we have our residual blocks with a bunch of convolution layers. Remember, there is no batch normalization in these layers because they had removed that. And then we basically stack these layers, okay, as you can see, based on the whatever is the number of blocks we give as an input. We give 16, which means there will be 16 of these stacked conv blocks, okay? And this is your residual or the skip connection, as we discussed earlier. And this model, then all we do is we create a learning rate, dynamic learning rate, okay, which will decay over time, which means it will start off with 1 e minus 4, means 10 power minus 4 is your initial learning rate. Then it slowly decays to 5 e minus 5 and then 2.5 e minus 5. Okay, that is the kind of dynamic learning rate we used, again, based on some tuning in terms of what worked well for us. Simple mean absolute error of the like high resolution versus generated image. Pixel wise, we just do a mean absolute error. And then we train it for, as you can see, 500 epochs. Okay, so this is kind of, okay, this is how the learning rate decreases over time, and this is your loss kind of slowly decreasing over time, okay? And then we create some code to do some inference. So you can see, hopefully this is visible clearly because, yeah, sometimes you have to like download the images and see it. But let's say this is the original image of a blue rose, probably fake, but this is like basic basic upsampling, okay, with bicubic interpolation. And this is our super resolution image. So hopefully you can see like here, the dew on the rose, right? You see it's kind of
Yeah.
blurred, but here it is much better. I hope you can see that, right?
No, I do see it.
Okay, that is good. So yeah, that was where it was kind of showing that, yeah, this is something which is definitely working. This is a flamingo, really bad resolution. And you can see like it definitely improves on it. So where here you can't even see the eye properly, but here you can start seeing it, right? And the idea is it is good, but it is still a bit blurry if you see overall. So the idea is, okay, can we make this even better? That is where the whole idea of the SRGAN came into play. Okay, so that is
Can I just ask a question? So with
yeah,
like
yeah,
the satellite images, I know you're taking a really nice image and comparing it to an older image. When you have something like a flamingo, right? You have this blurry flamingo and you're just comparing that with good pictures of flamingos and trying to put this, which is interesting and different, right? Because like if I'm taking a picture of a specific place, that place is the same place 10 years later, whereas these are different flamingos.
exactly. That's the thing. In this case, though, what we did was to do an apples to apples comparison. We took whatever was the flamingo, we corrupted it purposely, and then
Mhm.
we tried to see, okay, the actual flamingo image is not here, but we tried to see, okay, how close can we get to the actual one,
Right, and that's so
just
you
to
can actually measure it. Nice.
exactly, yeah, yeah. Because otherwise, yeah, it's all visual. So yeah.
Hmm. And
And then
we
yeah.
have someone asking if you'd mind sharing the code. Is that something you're able to do, or?
Yes, I will. I don't know where I should put this, but we actually have the full repository for. We have open sourced it on our GitHub. You can
Okay.
star it and bookmark it. I don't know where I should put this link.
Do you want to just put it in the chat? Because then it'll be in the chat on LinkedIn and people should be able to.
Oh,
I
is it? Let me see.
think so.
It doesn't show me. I'll maybe put it here in the private chat if you could post it. For me, it doesn't. I don't see
Oh, you don't
the
have the
option.
chat? Okay.
Yeah, yeah, I can see everyone's messages, which is good, but yeah, I can't post it. Yeah, you could share the GitHub, and
Perfect.
yeah,
There you go.
perfect, wonderful. So then the idea was, okay, we have built this nice model which seems to be working. Why not make it even better by plugging it into that SRGAN architecture where we use that pre-trained EDSR to generate the images and make it even better by plugging it into the discriminator and basically trying to make it better using the SRGAN architecture. So that is where we created the discriminator. As you know, in GANs, you have a generator and a discriminator. Generator generates the images. Discriminator tries to tell whether the generated image is fake or real. And both are playing in a zero-sum game. So we use the paper of SRGAN to create this code to generate the discriminator. And as you can see, the last, again, it will have a bunch of conv layers typically with your activations, patch normalizations, and so on. And the last layer is having one neuron in the dense because we want to predict a yes or a no, right? That is how a discriminator works. And then instead of creating a generator as proposed by the SRGAN paper, we just loaded our pre-trained EDSR model, which I just showed you above. Okay, that is our pre-trained generator. This is our discriminator. And discriminator is something which we just created now with this architecture, right? Bunch of conv layers, batch normalization, output layer, and then I will just skip through all of this. This is just visualizing the model architectures, right? So then comes our optimizers. Okay, so this is where we have our learning rate again, decaying over time. We have our optimizer for the generator. We have our optimizer for the discriminator, because again, both are individual networks which work in collaboration. Now, this is the interesting part. In the loss, we don't just use a basic MSE or a mean absolute error. We use a few losses here. Okay, so one of the losses is known as a content loss, perceptual loss. For that, we use a VGG model, a pre-trained VGG model. We cut it off at a certain layer. Okay, in this case, layer number 20. What is the reason for this? The reason for this is we want this model to extract features, in this case 512 feature maps, from the super resolution image and from the high resolution image also. And then we want to compare those features, those feature vectors together. Okay, so that is where what we do here is you can see the generator loss is having a binary cross entropy loss. Okay, that is one simple loss function which we use. The discriminator loss basically compares high resolution and the super resolution. And this is the content loss, where we extract the VGG19 features for the predicted image, the super resolution image. We extract the VGG models features for the high resolution image. And then we try to compare an MSE loss on those features instead of doing it directly on the images themselves. Okay, and then we have to train our network by doing the backpropagation manually. You can't put all these loss functions in a model.fit. Okay, so that is where we define our backpropagation loop manually with TF gradient tape. We have the batch of images which are low resolution, the input. We have the ground truth, high resolution. We create the super resolution images by passing it through our pre-trained EDSR network, which I showed you earlier. Get the predictions through the discriminator network, compute the content loss by passing in the high resolution and the super resolution. This is where we use the VGG network to compare, okay, the feature maps, compute the generator loss. Generator loss is simple binary cross entropy based on a pixel-wise loss, okay, between super resolution predictions. And then
DJ,
we use, yeah.
do you happen to know what the 12.75 was for? A couple
I
lines up.
think this is probably the normalization which is used for because this model was pre-trained on the ImageNet data, so the actual VGG model. So this is the scaling factor which is used to kind of get rid of that aspect because we are using it on new data. So I think that is what was proposed in the paper, and that is what we ended up using. Yeah. If you check out the SRGAN paper, it should be there in the perceptual loss section. And then this is we basically literally copied the paper. Okay, so the perceptual loss is basically content loss times 10 power minus 3 of the generator loss. Discriminator loss is from your prediction versus the actual. Get the gradients of the loss with respect to the layers. Do the backpropagation using your optimizer, and do this for 300,000 steps. Okay, and I'll just scroll through this quickly. Okay, so this is where we can see that the learning rate and the discriminator loss slowly reducing. Perceptual loss should stay somewhere between this. It shouldn't really fluctuate too much overall. And then if I show you some examples, so let's say this is EDSR, you can still see there are some blurry aspects here. They start becoming clearer here with the SRGAN, and I'll show more examples. This is a low resolution tiger image. This is SRGAN, right? And you can see that if you focus on this aspect, you see this is with the EDSR initial one. It is still a bit blurry, but it becomes more finer here, right? So that's the effect of fine tuning and EDSR using the SRGAN architecture. Flamingo, yeah, you can see it's much better now as compared to the initial EDSR. So yeah, that's where the hobby project came came in handy, and we ended up using it for the satellite imagery, where also it worked pretty well.
Oh, that's awesome. That's awesome. And so, were there any other interesting challenges that you ran into during the project?
The biggest challenge, I think, and that is where these diffusion models are also becoming very popular these days as compared to GANs, is again, GANs are like super data hungry. So if you don't have a lot of data, your model may not perform as well. So I think that is where the transfer learning aspect really helped us. Pre-training the model on a larger data set and then fine-tuning. But that's one of the main challenges. GANs are super data hungry. The other aspect would be, I think, compute, because these models do take a fair amount of time to run. That is where, with larger image sizes, it may take even hours to days if you are training it on really large images. So having a good GPU compute is necessary. In general, a Colab Pro should work well for most images less than, let's say, 100 cross 100, or maybe even 200 cross 200. But beyond that, that's where, yeah, you'll need a powerful infrastructure. I think those were the main challenges in general, more from an implementation perspective. The other aspect is like, yeah, understanding the research papers, looking for existing implementations if they are available, adapting it to your problem. That itself is a whole exercise.
That's a good point. Looking for existing implementations. Yeah, so are there enhancements that you're currently working on? Is this still...
We aren't working actively on it, but one of the aspects which we definitely want to explore sometime in the future, when there is, let's say, a fair bit of time, is to see if we can leverage some of the newer transformer based models for doing the super resolution, basically, because these papers have been released much recently. They seem to claim to beat the previous architectures. Of course, trying it on real data is a whole other story, but yeah, that is something which we would definitely want to do. And other than that, yeah, South Pole, based on the interaction we had towards the close of the project, was they wanted to use this to actively look at or study these areas, right? These, let's say, encroached upon areas, or these areas which are actually sensitive, and you need to preserve the wildlife or the forestry there. They want to take actions based on that. And the other aspect would be, yeah, if we could convert this into some kind of end-to-end system, let's say deployed somewhere, which could take in images at any point of time and give you the high resolution image. Right now, it is all just a basic pipeline, but that would be like the end goal.
Awesome. And so, what kind of advice do you have for somebody who wants to start working with super image resolution?
The advice would be you can start with exactly these papers, which are pretty interesting. You can start with even some of the code which is in that GitHub that can, because literally all you need is X and X dash, right? Where X is your low resolution images, X dash is your high resolution, and then you're trying to generate the super resolution. And then you play with these models, check them out, read up a bit on the research, because that really helps you build your understanding, especially if you want to modify things, because that's what we wanted to do some modifications also to see if it helps. And in this case, it helped. So the advice would be, yeah, start off with the simple models without GANs, because they're easy to train, and then go more complex with the GAN-based architectures, and maybe the architectures based on vision, transformers, and so on. Those would be the latest state-of-the-art ones. The other advice would be, yeah, get comfortable with a framework, be it TensorFlow, PyTorch, whatever you like, and then try to use that to do the implementations and try it on your own data sets.
And what are you reading? Like, and I'm sorry, you had no idea I was going to ask this question, but so you seem to do so much research on so many different topics. What are you reading like right now?
Right now, I'm actually reading as well as implementing stuff for a project which I've been working on. Can't go into a lot of details, but it is based on survival analysis, which is shockingly, there's not a lot of content out there. There is, but once you actually check that content, you'll see it's a rehash of articles of the same things again and again, right? So, yeah, maybe. Again, depends on the time at hand, but I'll write something in the future on this. But yeah, doing a lot of reading as well as implementations, because it's a real world problem which we're trying to solve on survival analysis, which is all about not just predicting if, let's say, a customer is going to churn or not, but okay, the probability of this customer churning over the next 5 months is X percent. That's literally what survival analysis is. So yeah, that's something I've been spending a lot of time on.
Nice. I took a whole semester long course on just survival analysis in grad school.
Yeah, maybe you could share something with me later on. So yeah.
Yeah. And so this was absolutely amazing. I really appreciate you putting it together. If people want to find and follow you, how can they do that?
Yeah, just search for me on LinkedIn. I don't use a lot of social media. I don't have a Twitter account. I want to close my Facebook, but it is linked to a bunch of, I don't know, apps and other stuff. So that's the reason it's still there. I don't go on there though. But yeah, LinkedIn is the best place. Feel free to reach out to me. I have hit the connection limit though, which is always a pain. I have to explain people what's going on with that. But yeah, you can definitely follow me on LinkedIn, message me if needed. Try to reply back as and when I get time. But yeah, that's the best place. Yeah. And GitHub, maybe. Yeah, I sent you the GitHub of the project. You'll find my username there also. Yeah, it's sad, but that's the only socials I have.
I think that's great.
For me,
yeah, awesome. Is there anything else that you were hoping to share about the project before we close off?
Overall, yeah, this is the main thing. I would briefly maybe show you the GitHub. I haven't added in the main README here yet. Just being a bit lazy because I've been busy on other things, but I will add that here. But the good part is if you go into the notebooks, you will find it very well documented with what was done for data sourcing and processing, what was done for modeling, what was done for evaluation. And the good part is if you go into each of these folders, you will find the details of, okay, what is the data which was exactly used? What does each of the notebooks do? I don't think you will find this level of documentation even when you're working in the industry in some teams. That has happened to me. So
that's beautiful.
Yeah, so we have added this, yeah, all thanks to our team. And yeah, feel free to check it out. Details of some of the models are also here. Yeah, that's the only other thing I had to share about the project. Maybe this comes handy to you someday. Yeah.
Yeah, awesome. Well, thank you so much, DJ, for coming on and sharing all of this with us. That was really awesome.
Not a problem. Glad to share. And yeah, thanks to everyone for being here.
All right. Yeah. Thank you, everyone, for coming. See you soon. Bye.
Thanks a lot, folks.